Good morning, everyone. Good evening, good afternoon, wherever you are in the world. Welcome to ICANX Talks, Connecting the World and the Universe. I'll be your host today, Professor Martin Thuo, coming from North Carolina State University in the eastern side of the United States. We continue our series this month, following the talk last week from Federico Rosé from INRS, and today we are privileged to have Andrea Alù from City University of New York. I will be joined by a panel consisting of Alice, the founder of ICANX, Professor Nader, and Alexander, and our challenger is going to be Wang Wei. Our speaker today, Professor Andrea Alù, is a very well-accomplished professor in the area of photonics and metamaterials. Andrea is a distinguished professor at the City University of New York. He's a founding director of the Photonic Initiative at the university, and is the Einstein Professor of Physics at the same university. He has very, very many awards, starting with being fellows of the NAI, National Academy of Innovation, the AAS, American Association Academy of Arts and Sciences, IEEE, MRS, OSA, and APS, among many others. He's the president of Metamorphos, director of the Simons Collaborations on Extreme Wave Phenomena, and is the editor-in-chief of Optical Materials. He's extremely well published in this field and has received many, many awards. I'll just highlight a few because his resume is too long. If I did everything, I'll take his time. He has won the Van Velle Bush Factor Fellowship. He has won the prestigious Blavatnik National Award for Physical Sciences and Engineering, and the NSF Alan T. Waterman Award, among many, many other awards. He received his Royal in 2001 and his PhD in 2007 from University of Roma in Italy. Then did a postdoc at Penn State, University of Pennsylvania, before joining the faculty at University of Texas at Austin in 2009, and before he moved to City University of New York. And I will hand over to our speaker to share with us today about extreme control of light and sound with metamaterials. Andrea?
Great. Thank you very much. Thanks for the invitation to speak here, and good morning, everyone. Good afternoon and good evening. Can you see my screen?
Yep, we can see it.
So today I want to tell you a bit of our research and the progress in the area of metamaterials and how these engineered materials enable control over light, sound, and other waves. I want to start by a statement. Wave phenomena are everywhere around us, and that's one of the power of this field of research. It's highly interdisciplinary and can enable us to control phenomena that happen in a wide range of scales and of instances. Light, sound, thermal fluctuations of materials, mechanical waves, seismic waves, water waves, even in the ocean, are disparately different phenomena, but at the same time, they actually follow quite similar mathematical rules, and therefore, oftentimes we can actually borrow from each other's fields and apply similar concepts to mold wave phenomena in extreme ways in various settings. Another interesting aspect is that waves and wave physics is associated with a wide range of grand societal challenges. Light, sound enable us to see, to image, to sense. They're associated with energy harvesting and wireless communications, among many other technologies that are fundamental in today's and in the future. Therefore, it's very important to garner control over waves in new ways. At the same time, the technologies that govern these wave phenomena are relying today on a quite limited set of materials. And one important drawback is that typically these materials interact quite weakly with waves, and therefore the overall response is limited. Hence, these technologies need to become bulky often, and overall are limited in the performance metrics. To enhance these interactions, we can rely on nanoscale engineered materials that we call metamaterials. This field, you may be familiar with it, has started, I would say, around 2 or 3 decades ago, and today is really flourishing, given advances in nanofabrication and in the understanding of the ways in which waves, light, sound interact with subwavelength structures, and the type of materials we can employ as basic constituents of these meta materials. The word meta comes from the Greek. It means beyond, and really the idea is to engage materials, but also nanostructuring, broken symmetries, shape, composition, alignment between these nanostructures to endow the new engineered materials with properties that are not available in nature and are very different from the constituents. Here you see some examples of optical metamaterials, but these same concepts can be extended to a wide range of wave phenomena. If I wanted to describe with 2 words how metamaterials work and why they are so powerful, I would use the combination of 2 things: the nanoscale resonances, the subwavelength resonance of the structures to incoming waves, and this happens typically through strong lead matter interactions of the constituents, plus tailored broken symmetries. The idea that we can control over multiple layers in the neighborhood of each other's nanostructures, the asymmetries that are associated with their geometry. And a good example, for instance, is to plot in this simple plot in which on the horizontal axis I have the frequency of excitation. Here I'm thinking about light, so there is the electric field E, and the response of the material that I can average out as the conductivity in this example, but this could be also the electric permittivity or other responses of the materials averaged over a volume. And we see how around the resonance this response can gain a wide range of values, and in general can also become a tensor, can become a response that depends on the orientation of the incoming electric field, that is a vector. I will use this notation in the following slides to show you how garnering control over this response and exploiting these wide variations in the values of the entries of this tensor allows us to manipulate in extreme ways light, sound, and other forms of wave matter interactions. So thinking of probably simplest example of a wave, if I drop a droplet on a water pond, I would form these circularly shaped wavefronts. This is a very common and well-known experience. The analogous phenomenon for nanoscale light would be placing a localized optical emitter over a symmetric isotropic surface. And going back to the same notation of the conductivity tensor, this means that the elements on the diagonal of the conductivity tensor are equal, or at least share the same sign. Under this assumption, indeed, if I put an optical emitter over such a surface or such a meta surface, I will find circular ripples of light waves expanding from the location of the localized optical emitter. However, if I can form a pond that is extremely asymmetric, for instance, that has the opposite sign of the diagonal entries of the conductivity tensor, the response I would find is actually very different. The waves, rather than going circularly away from the point of excitation, they actually expand along these hyperbolas, and in particular are much more confined along specific directions that depend on the entries of this conductivity tensor. As you saw in the previous slide, these also depend on the frequency of the response. So as a function of frequency, these strange waveform shapes will change. If I take the Fourier transform of this field distribution, I get this hyperbolic response that is very different from the circles that I would expect from a symmetric surface. So here you see the role of large broken symmetries in over the surface. One important peculiarity of this response compared to the other one is that the topology of this isofrequency contour, as it is called, of this Fourier transform of the fields in space, is open, as these hyperbolas have an open contour. And that openness is associated with very large interactions of light of the optical emitter with matter, with the surface underneath. In fact, you can quantify that interaction as the integral of this curve over all momenta, over all wave numbers. Being an open contour, being an open topology, this means that the integral can become very large. In principle, it's unbounded if I neglect the loss in the surface and the effects of non-locality over the surface. And the particularly interesting scenario arises when I am at the transition from an open contour like an hyperbola and a closed contour like an ellipse. In fact, this happens when one of the entries of that conductivity tensor goes to 0. At 0, the hyperbola has to shrink to transform itself into a circle. And for geometrical reasons, for topological reasons, this must go through a flat band like the one you see here because of the change in topology. In this regime, as you can imagine, the wave interactions are very interesting because, again, with the water wave analogy, you are throwing a droplet into this pond and see the waves go in straight lines. They are allowed to go only in a specific direction, and they do not expand, they do not diffract over the surface. This allows giant, extreme light matter interactions, in fact, the strongest you can get under these assumptions, and sub-diffraction imaging of a complex source, if it's not just a point over the surface. So to realize these effects, we can actually use patterned surfaces. This is work in collaboration with Peng Li and Rainer Hillenbrand, in which we took a boron nitride surface. Now to go into more practical devices. Boron nitride happens to support naturally a strong phonon resonance that comes from mechanical vibrations of the lattice of the crystal forming boron nitride, that in the mid-infrared range, when excited with light in this range of frequencies, supports its very strong resonances for electric fields vertical to the layers of boron nitride. Because we want our asymmetry to be in plane, we have to pattern this. So we can cut the surface into nanoribbons, and that allows you to have a negative response for electric fields parallel to the ribbons, but positive response of the effective conductivity for electric fields orthogonal to the ribbons because they fill these gaps. They work like small capacitances. And the effect indeed is to find this type of hyperbolic branches and even this canalized regime in which light couples to these phonon vibrations and drags even mechanical vibrations with the nanoscale light in sub-diffraction forms. Very exciting responses. Here, really, you see at play both light and sound at the nanoscale. Actually, with Guangwei, that is on the panel, we've been starting to explore this type of interactions a couple of years ago in the context of adding an additional knob to control geometrical broken symmetries. And that is when you take two of such surfaces, identical surfaces, but you actually twist one with respect to the other. adding the twist aspect and exploiting the fact that the nanoscale light is already very asymmetric on each layer, you can actually realize a reconfigurable propagation of these waves in extreme ways again. The way to understand how geometry plays a role in this context, we can look at the response of this bilayer as we change the twist angle that is on this vertical axis for fixed frequency. Remember, as you change the frequency, also these hyperbolas change. This is a broadband response, actually. But at fixed frequency, as I change the rotation angle, you notice that, for instance, if the two surfaces are 90 degrees rotated, so these ribbons are basically orthogonal to each other, the two hyperbolas cross 4 times. And if you make them close enough to be strongly coupled, at the crossing points, the hyperbolas actually avoid each other. They repel. This is called avoided crossing in the language of band structures. And the result is that the two hyperbolas form actually a closed contour. So you start from two hyperbolic surfaces, you put them close to each other, twist by 90 degrees, and you find the nanoscale light comes back to be isotropic, almost isotropic, circular in response. But as you change the angle of rotation, the crossing points move, and therefore this circle becomes actually more slanted. If you look at the other extreme, 30 degrees, now the crossing points are only 2. So the hyperbolas remain open. Of course, they are different hyperbolas, but they cannot close because there are no 2 crossing points that close the band. And as I said before, there is a topological argument to be made for which if you continuously change this angle, you must go from closed to open through a flat band transition. That reminds us, if you're familiar with condensed matter physics, with the electronic response of twisted bilayer graphene, that for a specific twist angle support flat bands for the electronic transport and superconductivity. Compared to that problem, here we have another knob, that is frequency. As you change the frequency of excitation, the hyperbola branches actually change their opening angle, and therefore you can actually continuously tune the special angle for which you transition from elliptical to hyperbolic, and you get these flat bands, and you get a broadband response over which, as a function of rotation angle, you can tune from elliptic to hyperbolic. To envision this response, in collaboration again with our colleagues C.W. Chu here and several others in China and Singapore and Australia, we have been looking at stacking twisted bilayers of molybdenum trioxide. The molybdenum trioxide naturally has been shown to support this form of hyperbolic waves, hyperbolic polaritons on the surface because of the crystal structure. The crystal structure of this material supports a strongly anisotropic resonance for electric fields along one polarization, and therefore naturally has been shown to be a hyperbolic metasurface effectively. In this case, just the nanoscale or atomic molecular scale structure forms that asymmetry that we are after. We don't need to structure it at the mesoscale. By twisting these two layers on top of each other, we can control that transition in the same way. And this is a plot of the same response I showed you before, but now using the parameters of molybdenum trioxide. These are full wave simulations at fixed frequency demonstrating the concept, and the Fourier transform actually shows indeed how the analytical modeling I was describing, the avoided crossing, actually match nicely with this transition from hyperbolic to elliptical. What's remarkable is that this is the same material. You are just twisting the two thin layers on top of each other and transforming in extreme ways the response to nanoscale excitations. And to demonstrate this, we can use a technique, microscopy technique called near field scanning optical microscopy, for which by placing a point defect on the surface, we can observe the optical fields excited by an incoming wave as it scatters on the point defect. This tip here can scan the fields and map the nanoscale response over the surface. So you see, for a single layer, we find hyperbolic wavefronts, but as we twist the layer, we can go from hyperbolic to canalized to elliptical at the same wavelength. So these are same materials excited at the same wavelength with the same type of excitation and point defect, but by twisting the angle between these two highly asymmetric crystals, we can get very different nanoscale response. What's remarkable is that these concepts can be translated at widely different scales and widely different wave phenomena. This, for instance, is work done on a macroscopic Lego metasurface. These are Lego blocks. These are actually pictures of these Lego blocks in which we pattern a moiré pattern that comes from interleaving two different surfaces at an angle. And by changing that angle, in which the two families of Lego blocks are interleaved against each other, we see the same type of phenomena. Here, of course, we don't use microscopy. We use actually a technique that also uses light. It's called laser vibrometry. Using laser lights, we can actually observe the vibrations of these Lego blocks as they're excited by a shaker. And we can see how the mechanical waves, elastic waves, travel on the Lego platform as a function of the loading, and how the similar topological transitions of the surface waves are enabled. We get more flexibility if we 3D print our structures rather than relying on Lego blocks. And this is actually the same type of experiments, but realized twisting two metasurfaces that support hyperbolic elastic waves, realized again by using resonators out of plane with an asymmetry. These dimensions Cx and Cy are different to realize the hyperbolic response. Over the single surface, we do find experimentally this hyperbolic propagation, and by stacking the two of them against each other and rotating, we can find the same type of topological transitions. These are actually experiments. This is the laser vibrometer that is measuring these vibrations that travel along this plate. These are all macroscopic scale phenomena, but they map what happens at the nanoscale with light and phonon vibrations in the crystal. And with this laser vibrometer, we can actually observe even how broadband this effect is, and how strong the effect of the twisting is even in time domain. As time evolves on the vertical axis, the broadband excitations over these elastic waves can be largely steered and detuned in shape. This basically is the analog of that water wave droplet experiment, but happening using a shaker over broadband shaker, like a chirp pulse over these twisted metasurfaces. Now, understanding the role of these wave phenomena, and specifically the role of broken symmetries, one legitimate question is, what happens if we make structures more asymmetric? So I showed you the response of molybdenum trioxide that naturally gives us this strong asymmetry that comes from very polarized phonon resonances in the plane of the interface with air. This corresponds in the language of tensors to a uniaxial tensor, a diagonal tensor that has different entries for different directions. This means this is because the two resonances supported by the crystal, the phonon vibration resonances, are detuned and orthogonal. But interestingly, there are materials in nature that can give us even more asymmetry. A good example is gallium oxide. Gallium oxide also supports a strong high-quality factor phonon resonances, but they happen to be not orthogonal to each other because the crystal symmetry is monoclinic. What this means is that now my resonators are not anymore orthogonal, and therefore the response of the material cannot be diagonalized, as in the case of monoamine oxide. It has these off-diagonal entries. The effect on the propagation of these phonon polaritons is quite remarkable. You can still find hyperbolic responses, and that's when the eigenvalues of the real part of this tensor have opposite sign. So this is kind of a generalization of what I said before for the diagonal case. But also, there are two additional phenomena that you cannot expect in a uniaxial crystal. The first is that as you change frequency, the hyperbolas must rotate their axis. And that's because the tensor is not diagonal. The eigenvectors associated with these eigenvalues with opposite sign change their reference axis, their symmetry axis with frequency. The second effect is that when you consider the presence of loss become non-symmetrically distributed. One branch lights up, the other one is less lossy, is more lossy. What this implies is that for the same loss in the phonon resonance vibrations, we will have one branch of the hyperbolas that suffers less from dissipation. We can dump all the loss into one side. And this makes sense because the lossy resonators are more oriented into one direction than the other. What is remarkable is that you can maintain the hyperbolic response. So you can make the response even more directional and stronger than in the uniaxial, more symmetric case. We have observed this phenomena in the using a prism from far-field excitations in collaboration with Alex Parman, Josh Caldwell last year, and more recently this year, actually, Guang Wei here is again first author of this work. We were able to observe in the near field using another material, cadmium tungsten oxide. The reason to look for different materials is that each of them have their own symmetries, broken symmetries, and their own frequencies in which these strong phonon vibrations occur. In particular, gallium oxide has a resonance frequency that is a longer wavelength that cannot be easily accessed with near-field microscopy. So we turned into this other material that has a higher frequency phonon resonance. The challenge of this material is that the asymmetry is less pronounced than with gallium oxide. So you see already these trade-offs and these challenges when we have to rely on natural materials. So the natural next step is to look for meta-materials, meta-surfaces in which we can engineer actually these asymmetries. We can tune the response at the frequency of interest. Of course, one way would be to start patterning these meta-surfaces at the nanoscale. What we started to do in this direction is to actually go back to acoustics, to the macroscopic scale, and go from orthogonal asymmetric resonances to non-orthogonal asymmetric resonances in which we control the angle. And indeed, now we can see at the macroscopic scale, very large axial dispersion, rotation of the hyperbolic axis, and largely asymmetric loss distribution. These are experiments, indeed, demonstrating this at the macroscopic scale. Same platform, but now we added more asymmetry. Now we can control this angle between the resonators and indeed realize this asymmetry in the propagation of loss distribution and this rotation of the axis of the hyperbolas. These are demonstrations for as we change the angle of rotation, how we can control both the axial dispersion, the loss redistribution, and the nature of the response itself. And in fact, we can demonstrate maximum asymmetry. There is actually a maximum you can get for a passive structure through this patterning of the resonances. In fact, one can envision this to be brought down to the nanoscale. These are just calculations, but demonstrating that controlling the resonances and controlling the angle in between, one can realize maximum rotation of the axis of the hyperbolas, maximum redistribution of the loss. That implies quite remarkably that for the same level of nanoscale losses in the two non-orthogonal resonances, as you change the angle, you can make the response stronger. You can let one branch of these hyperbolas travel further away, get the fields more confined, and suffer less from the intrinsic material loss that you are working with. So these are different calculations, changing the angle between the nanoscale resonators, but maintaining the same level of loss. And if you study the response to an optical emitter, what I was describing at the beginning of my talk, you indeed find that as you change the angle, this is the angle going from 90 degrees orthogonal resonators towards 0 degrees, how the interactions of an optical emitter with the surface, known as Parcel factor, this is the quantity that measures the light-matter interactions, can grow significantly thanks to this loss redistribution and the manipulation of the Venn diagram that again comes from rotating the nanoscale resonances. This can be leveraged for many other manipulation of wave phenomena, and in fact, this can be also engaged in quantum phenomena, collective quantum phenomena, nonlinear phenomena to generate, for instance, light frequency manipulation and many other technologies of relevance that I don't have time to dive into in details. What I wanted to bring up now in the second part of my talk is that more generally, the role of these broken symmetries can be engaged at the full scale with metasurfaces. This is a picture of a recent schematic of the review that we wrote of the field of non-local metasurfaces that really engage powerfully with the broken symmetries across an otherwise periodic lattice. As we introduce perturbations in which we control geometrical symmetries in a plane, we can realize quite extreme manipulation of the optical wavefront. And we have shown over the years various applications in which these phenomena can offer to enhance imaging and image processing over a thin surface. Let me give you a couple of examples of these that are quite remarkable and demonstrate really the power of these concepts. So this is our metasurface in which we control with a lot of degrees of freedom the symmetries, the broken symmetries at each pixel to enable counterintuitive manipulation, in this case of a guided mode. And this is work well in collaboration with Nanfang Yu here at Columbia, nearby in New York. The idea here is to engage a guided mode and leak it out through perturbations of the waveguide in unconventional ways. This is how the structure looks like. As you see, it's highly non-periodic, but interestingly, all these nanostructures are non-resonant. So overall, they act like perturbation across the guided mode that travels over the aperture, and they leak the radiation in a way that does not perturb the overall coherence of the entire aperture. They still maintain the overall guided mode aperture, but they can control with 4 independent degrees of freedom per pixel that come from the rotations and the strength elements, the way in which the light is emitted from each element or scattered out. And as examples of this, we can build with rational design this type of apertures, and we can realize, for instance, a single aperture that fed by one guided mode can produce up to 4 independent holograms that happen to exploit different polarizations. These are 2 channels for the polarized emission and at different planes of observation on top of the aperture. Another remarkable example is this formation of Poincaré beam. This is a sophisticated beam that focuses at some height of choice on top of the aperture, but that contains all degrees of polarization. So if you observe this focused beam at with different polarizers, you can see different portions of the beam light up. And this has been proposed as a way to carry information. It's kind of one of the most complex forms of beam excitation you can come up with, and therefore can carry information away from the surface. This is just to show you how this concept can be translated quite powerfully in different wave platforms. This is a millimeter wave leaky wave metasurface, uses the same principle, but here it's a macroscopic scale, and it's designed for 20 gigahertz for new forms of wireless communications. So we excite the surface from this point here. We spread the wave out to form kind of a uniform wavefront, and then in across about 16 wavelengths, we leak most of the energy out, and we can control the radiation in arbitrary ways, again with 4 degrees of freedom per unit cell of this structure. So here, this was designed to focus one circular polarization at a certain point in the near field and emit a Gaussian beam with a minimum waste at the height of choice on top of the surface. The same principles can be also used to tailor thermal emission. That is quite remarkable, because thermal emission is a form of incoherent light emission. Is of course the most common and widespread and cheap form of light, but it's difficult to tame. Of course, the one coming from the sun or from incandescent light bulbs, very common to us. But as we all know, this thermal emission features broadband, very broadband emission that is highly incoherent, unpolarized light. Can we tame this form of emission? Indeed, by patterning a surface, a passive surface at the nanoscale with these rational patterns that control polarization, amplitude, and phase of the scattered light, we can actually engage the thermal oscillations and tailor the spectrum of the emission, make it much more narrow band, and tailor the emission of polarization. These, for instance, are 6 different devices that are realized to thermally emit a narrow band beam that is highly selective in polarization, and we can scan across the entire Poincaré sphere. So these are this is a surface that emits just left-handed polarization or right-handed polarization for this one, and different linear polarizations of the output. This is a surface that is patterned to impart a gradient of to the thermal emission, and a spatial gradient, and also to impart spin to thermal emission. So this passive silicon metasurface, it's remarkable. Also this is done with silicon. We don't rely on any special material. It's CMOS compatible. Heating it up, it emits a directive beam that goes at an angle of choice and is selectively circularly polarized. So it has a non-trivial momentum, both linear and angular momentum of thermal emission. You can pattern more arbitrarily across the aperture, so you can create a lens that focuses thermal emission, or an orbital angular momentum, a beam that carries both the spin momentum in terms of circular polarization and an orbital angular momentum of light. as it emits. It drives these incoherent oscillations into a coherent beam that emerges from the aperture. Finally, this is work in collaboration with Neder Engheta. This is also on the panel, and Vincenzo Galdi. Several years ago, about 8 years ago, we proposed the concept of signal processing metamaterials, the idea of patterning metamaterial to manipulate waves not in spatial form, to manipulate the wavefront, but in momentum, to impart mathematical operations to incoming images. And one example of that is quite powerful for several applications is the idea of imparting derivatives to the incoming images that allows us to realize edge detection, to see just the edges, the borders of an arbitrary image as we see through a film. So the idea is to realize metamaterial films, passive, that in the same way our sunglasses can filter polarization, this would filter the momentum of light such that they let through only the edges of an arbitrary image. And of course, one of the important applications of this is to simplify and make less energy demanding and faster the edge detection and object detection for autonomous driving. The idea is to realize object detection by simplifying, feeding an image to a computer that is less complex by feeding only the edges. And this can be done at the speed of light, essentially without energy across a pattern in film. These are examples of measurements. These are changing the location of the surface. So I want to stress this basically allows you to get the edges of an image through the film without having to place it at a specific location. This can be moved around. You just have to see through this patterned film. And interestingly, if you add the polarizer in front of this image, you can selectively detect just specific edges. You can do form of polarization imaging added to the edge detection. Only the edges, for this specific design, only the edges aligned with one polarization of light comes through. Of course, you can also do polarization independent designs as desired. And in collaboration with Albert Polman and Neder Engheta, we have demonstrated recently that it's possible to add feedback to this idea. This actually builds on an idea that was demonstrated already at microwave frequencies by the group of Neder Engheta, but this is done now on a metasurface with at optical frequencies, basically adding multiple reflections and feedback from a metasurface that builds a kernel of a complex mathematical problem. We can, observing the output of this of the scattering from this metasurface, we can actually measure the solution of a complex mathematical problem here spelled out in this integral differential equation. And this again happens in a few cycles of oscillations of light. So it's a quite powerful form of analog computing that is built in this metasurface. In this paper, we envisioned even the possibility of going down to the nanoscale, building a single nanoscale object that, when interrogated with a complex waveform coming in, as the interacts with the object, the outgoing scattered wave encodes the solution of a complex mathematical problem of choice that is basically encoded in the shape and structure of a macroscopic object that can be at the scale of the wavelength of excitation. This also opens up to the opportunity of building more complex forms of analog computers in which multiple of these objects actually interact and feed each other's output. Finally, in the last 15 minutes, I will discuss the role of a different form of broken symmetries. What I showed you until now relies on broken geometrical symmetries, and we have seen the power of controlling, tailoring this broken symmetry at the subwavelength scales, and how this can control in extreme ways light and sound. But interestingly, there is another symmetry that is even more fundamental in wave propagation, known as time reversal symmetry. The fact that most commonly, and in all the devices I showed you so far, the waves obey this form of time reversal, for which if I swap the sign of time, I drive it back, I get the same solution of Maxwell's equations. This in practice implies that if I can send a wave from point A to B, I can play it in reverse and send it back from B to A. This symmetry can be broken, and is broken in many devices. In fact, it's useful to break it for purposes of isolation, of letting waves through a channel but not wanting to receive reflections. But typically, it's quite difficult to do. You have to break somehow the inherent symmetry in the channel. One way we found powerful to do to enable this type of broken symmetry is to tailor resonances, metamaterial resonances, with forms of symmetry breaking that come from mechanical motion or temporal modulations. A basic example of that, and this is now several years old, we demonstrated this in 2014, is the simple idea of starting from an acoustic cavity, symmetric cavity, it's a circular cavity, and load it with fans and move the airflow in this cavity at the specific velocity, very slow compared to the velocity of sound, but tailored with the shape and quality factor of the cavity to realize a form of isolation and circulation. So as you see in these simulations, sound that comes from this port actually goes straight into this port, isolating. There is no transmission of sound in this port. Actually, the contrast in transmission between these two ports is 10,000 times. But if you now excite from this port, because of symmetry, actually sound goes here, and from here back to this port. So this is a form of circulation that is highly non-time reversal symmetric, clearly, and enables quite exciting functionalities for acoustic technologies, in particular for sonar or for ultrasound technologies, in which we can enhance the resolution, both in time and space, of imaging by relying on the fact that you can send the sound through, but receive it at a different location. These concepts can be also powerfully translated into into electromagnetic waves, into light and radio waves. And the way we have explored to implement this is to use temporal modulations, modulations in time. So again, we start from a symmetric resonant cavity that supports degenerate resonances, left-handed, right-handed. This is completely symmetric, of course, and introducing again broken symmetry in this structure. First, we need to add a spatial modulation to the cavity that allows us to start playing with symmetries. This, of course, does not break any symmetry, as it is shown here. We still have symmetric modes, left-handed, right-handed. But now we can modulate in time the elements of this modulation, spatial modulation, and realize a form of synthetic rotation of the cavity. Here, nothing is mechanically moving, but by modulating in time with different phases, the different regions of this cavity, you can make this cavity spin. And this spin splits the degeneracy and create a form of broken time reversal symmetry that can be integrated into nanophotonic platforms to realize similar forms of circulation and isolation. Now, a laser light can go through from here, bottom to top, but when it comes back from the top, is routed somewhere else because it engages this synthetically rotating ring. And the same thing can be done in this photonic crystal structure, in which defects that are modulated in time spin effectively for the incoming light, realizing circulation. These concepts can be also brought to the chip scale and realize integrated circuits that realize forms of isolation and circulation, can be used to realize also asymmetric radiation of electromagnetic waves. These are all radio frequency components, so longer wavelengths that can be very useful for radar technologies and for wireless communications. And indeed, if you can build an antenna that breaks the symmetry between reception and transmission, you can also break the symmetry with which thermal emission is associated with absorption. I was talking about unconventional thermal emitters, but as long as they obey time reversal symmetry, they thermally emit in sophisticated ways in the same way in which they filter absorption because of time reversal symmetry. But if I can build antennas that can transmit and receive asymmetrically, then I can build a thermal emitter that can emit more than it absorbs, at least from a specific direction. And that can be useful to enhance also energy harvesting. We showed such a system in an antenna that is modulated in time. It's a leaky wave antenna that exploits, again, this idea of patterning the leakage of a guided mode into far field. And by imparting a form of temporal modulation, we indeed showed largely asymmetric transmission and reception of signals across the surface. These concepts can be also extended to arrays. This is an array of non-reciprocal elements that indeed are formed by synthetically rotating each of them and then patterning it into a metamaterial. And the idea of this was to mimic the physics of a topological insulator. That is a popular platform for condensed matter physics, very exotic electronic transport in these structures that let currents flow only on the edges, on the boundaries of these materials. Here we exploit the same physics, but on the boundaries of this metamaterial formed by synthetically rotating the unit cells of these structures. And this can be useful for, again, wireless communications to realize robust forms of routing of waves on the boundaries of an object. And in fact, bringing this back to the phonon polariton science that I was discussing at the beginning of my talk, we can build this exotic form of topological light over a domain wall of a photonic crystal and transfer it to boron nitride, to a phonon material. This is an experiment performed by Alex Kanikaev's group in collaboration with our group to demonstrate that it's possible to transfer topological non-trivial light propagation on the boundary of a metamaterial onto the phonon vibrations of thin film boron nitride. And this really shows, again, how at the nanoscale, light and sound can come together in non-trivial ways by exploiting patterning and broken symmetries on the surface. And to conclude, I want to bring this concept of temporal control of metamaterials into the idea that we can actually engage time as a form of interface that can be added to the spatial patterning I've been showing across my talk. So in the simplest form of resonance, we can think of a pair of spatial interfaces. This plot shows on the horizontal axis space, one dimension of space, on the vertical axis time. So a wave traveling along one dimension is an oblique arrow in this shape. And if it encounters the surface, it is partially reflected, partially transmitted. With two surfaces, we get this form of back and front reflections that form a resonance. In this type, this is really the basis of many of the metamaterials and metasurfaces I showed you, is the idea of engaging a nanoscale resonance, of course, over multiple dimensions in space. In these forms of scattering, frequency is conserved, and energy typically is conserved if there are no material loss, but momentum is impacted by the presence of these discontinuities in space. Similarly, one can think of manipulating waves using temporal interfaces. The idea is not to have a interface fixed in time, but at a specific location in space, but actually change the entire medium in space, but at a single instant in time. And it has been speculated over 70 years ago that the presence of such an abrupt change in the properties of a medium can realize the dual of a spatial interface called the temporal interface that actually reflects in time and realizes time reversal of the incoming signal. In this type of time interfaces, the frequency and energy can change, but the momentum is conserved because of the preserved spatial symmetry across the medium. Many groups have been working on this. In fact, one of the pioneering groups is the one of Nederengeta that has done a lot of exciting work in this area of combining temporal interfaces, and also he envisioned these 4D metamaterials that combine 3 dimensions in space and 1 in time to manipulate waves in totally new ways. But let me show you what we recently done in this context. And I want to give you a picture of this again in 1 dimension. If I have a spatial interface, if I have an abrupt change in the properties of a medium in time, I get in space, I get a reflection of my signal. In common ways, if you think of a mirror in front of you, typically you see your face reflected, and if you speak, you hear your echo in the same order of the sound as you speak. At the time reflection, the entire medium changes in time abruptly and strongly, like in a mirror, large impedance mismatch. This has to happen abruptly across the entire medium. In the simple sketch I showed you, what we expect in such an event is that you actually, in some ways, see your image time reversed. So you would see the back, if you could think of a hologram, 3-dimensional hologram that is going out and reflected back. And in terms of the echo, you would hear your voice time reversed. You would hear the last bit of your sound blip before the beginning, because it's reflecting back in time. And the first demonstration of this event was done by Matthias Fink's group a few years ago. And he showed this beautifully again in water waves. Let me go back to the beginning of my talk. This beautiful experiment, the image you see of that face goes out, but then after a kick of the water front, the wave comes back, time reversed, and forms back at the beginning of the movie. Recently, we built a metamaterial that allows us to observe this for electromagnetic waves, for photons rather than for water waves. Of course, this is a lot more challenging because we need to change abruptly in a controlled way and in a strong way the properties of the medium in which the signal is traveling. We do this by connecting and disconnecting reservoir capacitors from a long transmission line waveguide. This is how it looks. It's a meander line, 6 meters long, and you see all these switches that connect different parts of the circuit. They're triggered all at the same time and connect to external capacitors that change drastically the effective capacitance of the medium. And indeed, we can see at the input port, this is the input signal. It's a broadband asymmetric signal. The time reversed received signal is actually preserves the symmetry. So we receive first the last part and then the first part, because the signal has been time reversed. Interestingly, the opposite, after a while, we receive also a spatial reflection because the medium has changed, so it's mismatched at the output port. So we get some spatial reflection that preserves the same symmetry as the input. We also observe this frequency translation. I forgot to mention, you see from this plot, this sketch, that one other aspect of the time reflection is the change of colors. The fact that you change the medium but preserve momentum implies that the signal is abruptly translated in frequency. And we see this also in our experiments. Indeed, the signals are stretched in time. They preserve the shape in space, but they're stretched in time. And indeed, we see this broadband frequency translation of the signals across the entire spectrum. This experiment is basically frequency agnostic. It really happens at an instant in time, much faster than the involved frequencies of the incoming signal. You can pair two of these interfaces, as I was mentioning, and this implies the form of a resonance in which the signals, time reflected and time transmitted signals, interfere against each other, and you see this typical alternating zeros and peaks of the reflected signals as a function of frequency, typical of a Fabry-Perot resonance, but this is a time form of Fabry-Perot resonance. You can change the duration of the temporal slab, of the temporal Fabry-Perot, to make sure that you filter a specific frequency in the reflected signal. And the last experiment I want to show you is how, based on this platform, we can powerfully mimic the form of collisions between photons. So we can, you're familiar with how two masses collide against each other, and you can control by tailoring the geometry the form of this collision from elastic to inelastic, destructive or constructive in terms of energy. Photons typically they pass through each other. They do not interact in linear systems, but in our time interfaces, they can actually experience a sudden non-emission effect that introduces photonic collisions and controls them. So by tailoring the phase of the photons at the moment of the time interface of this abrupt change in the material properties, we can tailor the form in which these photons interact with each other. We can mimic elastic collisions or destructive or constructive forms of interactions. And indeed, you see here, as a function of phase, we can control the level of energy that is contained into the output signals. Here we are interfering two signals that come in from opposite sides in our medium, and then we abruptly change the properties of the medium. As a function of the phase between them, we can tailor the amount of energy that is left in the system. Of course, the gray lines here correspond to the cases in which we do not impart the time interface. And of course, the photons go through each other without any interaction. These are actually simulations demonstrating what I've described. These probably are more evident, more clear. These are the same signals that are interfering against each other at the moment of the time interface. The only difference between these two simulations is the different phase between the two signals. And you see how indeed in one case, the output from one side is zero, in the other case is actually amplified. And these are experiments demonstrating the same principles. Indeed, you see how here we tailored the structure to have destructive collisions, and basically we are left with zero reflections at the port. But when we change the phase of the input, we get actually an amplification of the output from after the collision. Let me stop here. I just want to summarize my my talk, saying that metamaterials offer a really interesting playground to manipulate waves and control their interactions with the matter. I talked about sound, radio waves, heat, nanoscale, optics, and briefly mentioned also the implications for mechanics and quantum phenomena. It's interesting how all of these can come together, described by the same laws of physics or similar laws of physics. They also have remarkably different microscopic phenomena that they control, and therefore a wide range of technologies and applications that they can benefit. I want to thank my group, and the City University of New York support for we're actually in a beautiful building in Manhattan, and I welcome all of you to visit if you happen to be in the area. Thank you very much again for the invitation, and thanks for the panel for staying, and I look forward to the discussions coming up.
Right, thank you very much, Professor Andrea Alù. That was a fantastic, very rich, very, very diverse talk. So we are very happy to have you here. On behalf of the host and on the panel, let me introduce our panelists. Of course, one of the panelists is Professor Alice. She's not new to this platform. She's the founder. She's well known in the community, so doesn't need much introduction. Our next panelist is Professor Neda Egatas, who has been mentioned quite a few times in the talk. And he is the Ned William Lanzi Professor at University of Pennsylvania. He's an expert in photonics, very, very broadly in photonic, metamaterials, electrodynamics, microwaves, and many, many other areas. He received his BS in Tehran and then moved to Caltech, where he got his master's and PhD. He has a lot of awards. I'm not going to go through all of them, but I wanted to mention specifically, he's also a Vannevar Bush Faculty Fellow, awardee, and has won the Isaac Newton Medal and Prize from the Institute of Physics in the UK, and is a fellow of many, many societies. I think there are about 8 or 9 of them. So we are very happy to have you here. Our next panelist is Alexander Kanikaev. Those who know Dr. Kanikaev, he is actually one who introduced the concept of photonic topological insulators. So we are very, very privileged to have him here. He received his PhD from MV from Nosov in Moscow State University in 2003, then moved from Moscow to Japan, to Hash University, where he did a postdoc and rose through the ranks. Then from there, he went across the Pacific into University of Texas at Austin, working on infrared photonics and plasmonics, and all dielectric metamaterials, sensors, and graphene photonics. He then moved in 2013 as a faculty member to City University of New York. He's also very, very well recognized and has many, many awards. He's a fellow of Optica, and also has for his awards, I'm going to mention one that is pretty significant. He got the NSF Special Creativity Award in 2021. Our ex-challenger is Wenwei Hu from NTU in Singapore. He's an assistant professor in electronic and electrical engineering. He received his PhD in 2020 from NTU, from National University of Singapore. And before that, he got his bachelor's in physics from Harbin University in 2016. Though he's a young faculty member, he's extremely accomplished, has 70 papers, over 70 papers actually, with quite a few in Nature Photonics, Nature Nanotech, and on all those high impact factor journals. His work has been named as a top 10 breakthrough in physics in 2020 across different platforms, Physics World, Optics, and Photonic News. And also in 2021, he had a top 10 breakthrough in optics in China. He has also been named a Rising Star of Light in 2020. And those who know, we host that award right before the Young Scientist Investigator right here. We also have a special guest today. We have Professor Nicholas Pepper. Nick is extremely accomplished. I don't even know where I could start. He's from national academies to fellowship across many, many awards, mentored hundreds of students, and his proteges are all over across the world as faculty members. So Nick, thank you so much for being our special guest today. And so I would like to give the first chance to our ex-challenger to ask any questions that they may have.
Yeah. Hi, Andrea. Hi, Andrea. Can you hear me?
Yep.
Yes, very well.
Yeah. Okay, great. Thank you for this very, very interesting talks and a lot of exciting new science and technologies. So I just saw from online that we already have like more than 14,000 audience online worldwide. So most of them probably are the student, undergraduate student or graduate student. I would like to ask the question from their curiosity that what kind of technologies or the key applications that you can expect, that we can expect from these metamaterials in the both near term, like 5 years, or in the long term?
Excellent question. Yes, it's a very exciting field actually, in which several of these ideas are translating at the moment, transitioning into technologies of various types. I would say the ones that are more mature are the ones that rely on controlling radio waves and optical waves at the near infrared range. There is a lot of excitement around, for instance, these millimeter wave technologies to enhance drastically the bandwidth and the metrics of performance of our radio and wireless networks, also in conjunction with the wireless communication protocols that are being grown around these new forms of technologies that control waves. There is the growing field of reconfigurable intelligent surfaces that is relying on some of these concepts and is taking over, actually, merging with the field of metasurfaces to control waves in new ways. These lower frequencies have the big advantage of relying on the possibility of strong manipulation of the electromagnetic properties of the medium and modulations in time that can be very effective at these lower frequencies. At higher frequencies, there is still, so in optics, there is more to catch up in the context of modulations. That typically temporal modulations either are relatively much slower compared to the very fast variations of the fields, and also are limited in terms of the strength of this of the modulation amplitude. But for static metamaterials, there is a lot of exciting development. There are several companies and startups that have started to translate these technologies into the field of augmented reality, of LiDAR technologies, manipulation of light wavefronts and their control. That would certainly benefit with having more with external control reconfigurability of this platform. And if we think in terms of longer term, in let's say 10 years from now, I think also the fields of computing that I was describing and of quantum phenomena and nonlinear interactions can become extremely powerful. I didn't forgot to mention also the field of acoustics that has also been very interesting, actually very friendly with field of metamaterials, and has been benefiting from many of these technologies for applications in controlling sound, in isolation, and in steering of acoustic waves.
Okay, yeah, thank you for this answer. And I will ask probably the next question, which is more like a fundamental viewpoint of the metamaterials. So as you have an excellent class on these metamaterials in SRT and in CUNY, and I attended and a lot of physics there. And before the birth of the metamaterials, we have the scientists that have studied the theoretical systems like the gratings using this coupled wave analysis or rigorous coupled wave analysis, and then they slightly change the periodicity to the photonic crystals, and now we shrink this periodicity to each subwave level to form the metamaterials. So I want to ask that in your viewpoint, what is the next trend of these materials, and even after these things of these materials, what is the next platforms can extend historical investigation of these theoretical systems?
Okay. There was a little bit of sound issue. I'm not sure that I understood completely the question. I don't know if the other panelists have the same problem. But if I understood, can you hear me? Yeah. If I understood,
sorry for that.
There is one issue with the microphone, maybe. But maybe if I understood your question, you are you asked about the role of patterning at the subwavelength scale in the context of TMDs,
no. Can you now hear me well?
No.
Can you now hear me well?
Still,
Guangwei, you have a little bit, sound problem. You can, remove your earphone. Maybe use your microphone directly. That should be better. We can first, Martin. Maybe we can first go to the audience question. Yeah.
Yep.
You see that
the audience question.
Yep.
Yeah.
There is a question from the audience. This is from Chengzi. They say it's an interesting talk. Do you think a broadband achromatic metagrading with a wide angle diffracting can be realized, since there is a trade-off between dispersion and the bandwidth?
Great question. Yeah, that's one of the challenges, especially as we go forward in this field of metasurfaces, and we basically metasurfaces for controlling the wavefront and go into applications. You talk to customers and companies, they typically tend to have many requirements on the metrics of performance. The devices I showed briefly in my talk are all actually quite narrow band. In fact, one advantage they have is that they avoid to scatter light in unwanted ways out of band of the response. And this is absolutely a challenge, as was mentioned in this question, about the unwanted achromatic aberrations of metasurfaces. Typically, the start of this field of science was based on trying to squeeze the response of a lens into a very thin lens or a very thin structure or other functionalities for optical devices. But as you squeeze the volume, typically you sacrifice bandwidth. The response will have an unwanted dispersion. You can prove that ways to control that trade-off exist, but typically you have to sacrifice, again, footprint. So by making the structures larger or adding multiple of these surfaces, you can somewhat mitigate that control. The path we have been pursuing recently is really the idea of engaging these perturbations of geometrical symmetries rather than relying on patterned resonators as more conventionally done in the field of metasurfaces. Using perturbations, you have the advantage that out of band, these surfaces basically become transparent. So you can actually stack, maintaining a low profile, multiple of them, and we have shown in a few examples stacking of 3-4 of these surfaces, both at radio waves and at optical frequencies. You can get multiple functionalities. Each of them is tailored for a specific narrow wavelength range, but they are transparent to each other. So that's one possible solution. Again, it probably will become difficult to span multiple octaves, and therefore there will always be some form of trade-off between complexity, I would say, and bandwidth. But at the same time, there are many applications for which one can happily trade some bandwidth for the extreme responses and the extreme flexibility of the control that these surfaces can provide. So it's a flourishing field with a lot of opportunities, and these are also new developments. So I believe there is a lot to do in this area to enhance the technologies further.
Yeah. If I can ask another question, this is Professor Yuri Gogotsi, very well known for 2D material, and his question is: what is the possible role of new materials, e.g., 2D materials, with different optical properties in achieving better control of light and sound waves?
Great. Thank you, Dr. Gogazzi. Great question. Yeah. So at the beginning of the talk, I was showing the opportunity to engage materials like gallium oxide, boron nitride. We have also done work on calcite that are not necessarily known for this nanoscale optical manipulation. Right? They support these strong phonon resonances at specific wavelength ranges, and they become quite powerful in demonstrating some of these strong interactions of light with sound, with this kind of microscopic sound vibrations. But this really shows the degree of flexibility we have in exploring new material platforms and bring the concepts of metamaterials into these platforms. Dr. Gogotz is very famous, world famous for his work on MXene. And I don't know if there is a lot actually done in this area, but certainly this is a very interesting opportunity. In general, empowering these breakthroughs in material science and combining them with nanoscale patterning and engaging basically material engineering and nanophotonic engineering on the same platform is very powerful. We have done some of this, for instance, with multiple quantum wells in the recent past, exploring these 2 degrees of freedom of the photonic states and the resonance states that can be engineered even at the electronic level to demonstrate new forms of nonlinearities. And I believe this is really scratching the surface of very powerful opportunity. So coming together, photonics and material science is a great way forward for the field.
And actually, if I can chime in a little bit there, to follow up on that question, just not 2D materials, but if you think, when I look at your work on heat and light interactions and how we can complement those two, do you think there is opportunity to even use things like liquid-based metals that form very thin nanometer scale heterogeneous or graded oxide as a pathway to bring in another aspect of generating an in situ sound wave?
Absolutely.
On the 2D material, is that something that can be explored?
Absolutely, yes. And I've seen actually some initial work in that direction. Actually, it is very exciting. More generally, I think empowering these opportunities that come from new material platform. I was talking, for instance, about the fact that we're missing tools to get strong and fast modulations in time as we go to optical frequencies or higher frequencies in the terahertz. We miss the basic element of the switch as we go up in frequency. And this is something that really working together with material scientists and looking at the different platforms available can provide totally new directions. There is a growing interest in looking at liquid crystals and phase change materials in this context. And certainly these are all explorations that bring together. The beauty of this field of metamaterials is that it's highly interdisciplinary. It brings together many different expertise and wouldn't be so successful and so exciting if not for this level of interdisciplinarity.
Okay. Very good.
Yeah. Can I answer the question?
In your work on gallium oxide, I'll be reaching out. We can discuss a little bit about gallium oxide and the liquid states. All right.
Yeah. Can you hear me?
Yes. Now it's better. Yeah.
Okay. Yeah. I just want to ask that question again. So you know that the metamaterial is essentially to study these periodical systems, and I would say that is continuous the continuum of these scientific efforts to study these periodical systems from the gratings, photonic crystals, and nowadays we use these metamaterials. Basically, the periodicity becomes smaller and smaller. So I would say that in your vision, what is the next platforms we can study these systems, and what is the next trends even after the metamaterials? Sorry, I'm probably thinking too long.
No, this is excellent. Certainly great Great question, and there are many directions that I believe are really exciting. I was talking a little bit about this introduction of time into the box, and Professor Enghet actually here on the panel has done pioneering work on that combination of time and space interfaces, and really this probably opens a lot of exciting opportunities, especially as the technology matures and we can bring together all these combination of phenomena, leveraging both the space and time reflections and interference between waves. Generally also bringing together concepts from other fields, right? The impact that has come from learning from condensed matter. I showed a couple of examples of topological insulators or of flat bands in the context of photonics. There is also a lot of exciting concepts that come from quantum mechanics, concepts of parity time symmetry. I didn't have time to discuss. And all of these are really opening new directions every day in the context of, from the old school of photonic crystals. Really, the field of metamaterials has been basically reinventing itself over the years, borrowing from concepts from other fields. And I'm optimistic about this continuous growth and expansion and the impact that this field can have.
Thank you.
Okay, any other panelists?
Can I go next? Yes.
Yep.
Well, good morning, good afternoon, good evening. First, I want to thank our speakers, Professor Andrea Alù, for a fantastic and fascinating and inspiring talk. Andrea, that was beautiful and great set of results and wonderful and elegant outcome. Thank you. And also, I want to thank Professor Alice Zhang for organizing this series of talks, and Professor Martin Tuo for moderating it, and also the other panel members, Professor Alex Khanikayov and the challenger, Professor Guang Wei Hu, and our dear friend and special guest, Professor Nicholas Pappas. It's good to see all of you here. Andrea, I have a couple of questions. In the early part of your talk, when you mentioned about these beautiful results you have on the twisted bilayers, and you said, by having that twisted bilayer, you can actually very nicely manipulate the dispersion for the wave number that you have. What would happen if you also add another knob into your system by introducing DC magnetic field to those structures and creating other interesting, asymmetry there? What would happen? Would it open up a quite interesting direction as well?
Absolutely, that's an excellent question. In fact, that's what's interesting of magnetic bias, of biasing with the DC magnetic field, the materials, of course, that respond to this, so magneto-optical materials, is that this form of broken symmetry breaks time reversal. And the one of the twist or any geometrical symmetry breaking obeys time reversal. So what's remarkable is that these two effects can be combined in ways that are highly non-trivial, because on one side of the Venn diagram, they can sum together, but on the opposite side, because one is odd and one is even, they can cancel each other. In fact, just with Alex Khanikayov, we have done an experiment. I mean, we have a paper that described this in a photonic crystal, in which we play. It's not about twisting, but it's about chirality and basically anisotropy, like so broken geometrical symmetries at the level of the individual unit cell. But we did show that it's possible to balance the two on one side of the Venn diagram and not on the other, because you exploit the different nature of the two. So certainly, yeah, these knobs are all. That's why I find fascinating how the role of these different types of broken symmetries that one can empower and combine in the same platform of these metamaterials. Certainly very powerful. Thank you. It's very inspiring.
Wonderful. Can I ask one more question, if the time allows? Andrea, you also showed beautiful results for your thermal radiation. That is very nicely you basically engineered, very nice, as a function of wavelength and polarization. What would happen? That's quite fascinating, what you showed. What would happen if you actually, in that system, you change the temperature of your system? Would this whole thing, moves in the wavelength quite nicely, the way you have done it?
Yeah, great question. No, unfortunately, at least for now, no. In the sense that the photonic structure is fixed. So we will get the thermal emission at the same frequency with the same features. The temperature change would modulate the amplitude of the emission, because we basically sample the Planck's law distribution. So you just shift the Planck's law, and then we suppress everything else. We just keep that peak. So there is an optimal temperature that gives you the maximum emission and we try to operate at that temperature. We can change it. We have a heat stage that controls the temperature. We try to operate at the temperature that gives you maximum emission. But as you change it, it goes with the typical T to the 4 law, but it stays fixed. But this question, of course, it's excellent because it brings to the next stage. The whole point of doing this is for us is to demonstrate that we can use the concepts of metasurfaces without having to rely on a bulky and highly coherent external source. Now we have a laser. Typically, we have a laser. We shrink the device, but we still have a bulky laser outside. Now we can engage the cheapest form of optical source. It is incoherent oscillations of matter. But of course, the challenge is, can we tune it? And that is something that goes back to also the questions we heard before. And for the moment, the answer, unfortunately, is no. But the idea would be, we are actually looking into ways of at least switching between 2 or 3 different states. But in the long term, and this probably is something that we need help with many of you guys on the call, and in terms of also material science, is to be able to tailor the pattern locally and array structure, maybe with MEMS, with macromechanical structures, to reconfigure the pattern. Then really we would be able to tune and shift. Temperature alone doesn't help us.
But if you also combine your idea of reconfigurable intelligent surfaces with your with your thermal aspect, that you can have additional control. That's beautiful.
Yeah. Thank you. But of course, the higher frequencies is more difficult. But yeah, I mean, maybe at low temperature would be really interesting.
Thank you. Thank you, Andrew.
Okay, can I have a question?
Yeah, sure.
Hello. First of all, thank you for having me. It's a pleasure. Andrea, always pleasure to listen to your great talks and, of course, very impressive results. So I wanted to follow up on quantum question, which kind of naturally brings quantum aspects to kind of this metamaterials field of research. So he asks, what's the next if we keep shrinking scale of patterning, and apparently at some point we will hit some quantum scales. Quantum phenomena will start to play some role, quantum confinement at least. And I wanted to ask you what you think is the broader future of quantum aspects in the field of metamaterials. Because as we know, like we are going through the second quantum revolution as of today, and hopefully we can potentially move from purely classical aspects of metamaterials to some novel quantum phenomena, maybe some quantum applications, very beautiful computations that we have shown, which are purely classical. Can there be maybe some hybrid quantum meta-surface computing? So what do you think about this?
Absolutely. Excellent question. Yes. And my short answer is yes. This is an extremely exciting avenue. And I think there are a lot of opportunities, untapped opportunities. I'm very excited about many of these. We have started to look into these directions, and I think more synergy between the quantum computing world and quantum materials and the metamaterials, metasurfaces would certainly be exciting to push this forward. I agree many of the things you discussed about the computing, about the quantum phenomena at the nanoscale that allow us to engage. In fact, many of the motivations for this research come from that vision. That, for instance, now we have shown we can drag light and sound at the subwavelength scale. As we go into the regime of a few photons or entanglement, can we map the same functionalities and tailor in new ways quantum information with these forms of extreme photonic or polaritonic, I would say, material and light engineering. There are also extreme challenges, right? The quantum computing, for instance, is very sensitive to the coherence, and material loss is extremely important. Right now, the field of quantum computing is divided in two camps, the superconducting camp and the photonic camp. Both of them can largely benefit, and in some ways have been borrowing a few concepts from metamaterials. The supercomputing, for instance, has started to look into temporal modulations to realize non-reciprocity that requires certain metrics that conventional non-reciprocal technologies cannot offer. The field of photonics, of course, can largely benefit from this structuring, but at the same time, we need to do better in the form of platform compatibility with these technologies that are very sensitive to maintain the coherence, very low loss. So it's an exciting moment to be in this field, and there's great interest and great opportunities coming up also for the new students that are joining the field. So I'm very optimistic, and I look forward to seeing more in this area.
Excellent, thank you.
Any other questions from the panel?
Nicholas, please.
I know that Alice is looking at the clock and says that it is past time, but I want to thank you, Andrea, for an incredible talk. I have followed quite a few of the ICANX talks, and I can tell you this is probably in the panel. It's just incredible to have Newton and Einstein together today. It's an incredible panel. It shows the convergence of the field. It shows that there are no barriers anymore. But what I liked about your talk, Andrea, and we miss you and Alexander very much here at UT Austin. You both came through here. What I like is that you were able to show that there are applications, because many people in the materials in the metamaterials field, they talk their physics and they are happy, and those of us who understand are happy, but we don't see the applications, and you were able to show the applications. So thank you for this, and I'm glad you are continuing to do this great work. Thank you.
Thank you, Nicholas. I want to thank you for your kind words, and also I miss the times that we were neighbors. But anyways, it's great to see you, and thank you for coming and to the panel. And I really want to thank again all the panel. This is amazing to have you here. And
okay, not finished yet. Okay, Andrew, also I have questions. I'm a panelist. Okay, yeah, Nicholas, I couldn't wait, till the end to ask the questions. So, Andrew, I was not a photonics field, but we met several times online, right? Yeah, for the rising stars, for other issues. But I'm very curious. You're always moving some new direction. Yeah, the new place, the new field, something, so what's the driving force for you? You are Einstein professors, you already well, established, but you still try so many new things. And almost every time I hear something from you, it's new. Yeah, so what's your driving force?
Thank you, Alice, very kind. I would say what drives me, and I would say also this field, is really the curiosity-driven explorations. That it's really exciting to see that we can manipulate waves in ways that you would think are not possible, or at least understand the bounds, push the boundaries. Since this field started And I had a great mentor, Professor Engeta, that really has shown this many times over many years. Really, it's a beautiful combination, as Professor Pepas was saying, between the curiosity-driven physics aspects and the possibility of making an impact on technologies that is not too far away, can be used. So this is what really drives me, and sometimes it literally starts as puzzles, like, would this be possible or not possible? And then the fact that one can do it, and sometimes even do it, as I showed, with the Lego blocks, right? It's not necessarily some extremely sophisticated. I've been lucky also to be here at this new lab since about 4 years, and really have a white canvas to build a dream lab in terms of trying this and having nanoscale light sources that are very powerful, like high power lasers and laser vibrometers to test the elastic. So this also helps a lot, going from the kind of paper and pen type of investigations and questions to really having setups, proof of concept realizations, even interactions with companies that can take this into the product.
Okay, great. Before you answer, I'm thinking maybe all these pressures from your great colleagues. You see, in Austin, you have a Professor Nicholas Peppers as your neighborhood. Yeah, you have Alexander, you have Nate, all these friends. Now you can move to New York. You also have Professor Peppers who was listen to your talk. So give you pressure. That's the reason. Okay. Yeah.
And also, I think, and also those students who ask very stupid questions and enjoy those scientific interactions with Andrea. And I enjoyed a lot in New York and also in Austin.
Yes. Thank you.
Alice, let me add something. I was going to send it by email. I look at the panel, and we are all born all over the world. And that is important. It shows that the whole world is coming together to solve truly important problems that will allow our citizens everywhere in the world to have a better life. And I think that's very important. This is not Chinese, this is not American, this is not European. It's everybody here. Thanks.
And let's hope, I totally agree. And let's hope actually that science can help us bridge difficulties and a lot of recent challenges geopolitically. Also, the issue with immigration here in the US that is getting tougher, and we benefit from this exchange. One way is a great example. He spent a lot of time in Austin, in New York with us, and we really hope that these borders continue to be a frequent exchange. And in that context, given how many people are connected, I welcome everyone. If you pass by Manhattan, any country.
And actually, Andrea, I was going to thank you for on my concluding remarks, because when you show that you can use Legos to do some of the work that you're doing, it is pushing a theme that we've been trying to get across on this platform, that science is not just about the tools you have, it's also about the ideas. And sometimes the simplest tools can give you the best, most beautiful discoveries. When you show how you built your meter-long meta surface, and you have the beautiful copper surfaces and all that, it's communicating a message to the young scientists. Because when you look at your data and you look at metamaterials, we always tend to think about very high precision engineering, very advanced tools, and to see that you can get the concept from a wave point of view. It is whether it's a sound wave, whether it's light, whether it's in your introduction when you're talking about water waves. When you bring that from such a fundamental level, I want to thank you very much, because for our colleagues in Africa, sometimes they feel they don't have a lot of resources. From our colleagues who are in Southeast Asia or some other countries where they're not very advanced equipment, we would like to share with them there are brains everywhere, and there are more than 5 billion
So,
of them.
Martin, yeah, actually,
Less
I
than
want to
5.
repeat this,
Yeah.
with you. Yeah, just Professor Nicholas pointed out a very, important thing. A factor on IKX. This is IKX, the cloud and universe. We want to get everyone who loves science, who enjoy all these, high tech issues to get online. Like Martin says that we promote, the science and technologies. Everywhere has the best, technologies or best tools, right? Even best environmental teachers, but all there have a brains, right?
Yep.
But all these brains can be inspired by you. That's good, right? That's anything can be happened here. So I like the X. Yeah, we try to promote X everywhere and get people to get connected by X.
Yeah, very good.
Okay, Martin. Yeah, that's my
Right.
comment.
I think we've ran a few minutes over the hour, but it's okay. The talk was very good. So I want to thank everyone for joining us. Fascinating work, Andrea. Really great, and I hope that we'll have even more follow-up after this. And
I want to thank again everyone on the panel that came, and I know you are all very busy and very successful. I'm honored that you are there, and also everyone that attended the talk and all the great questions.
Thank you. And if we were in a live presentation, Alice and I would have walked and handed you this beautiful certificate. Now I accept it as a virtual. We'll be sending it to you, and we're very, very grateful for gracing our volume 135. And also for everyone who's online, please join us next week when we have Patrice Simon, who's going to be joining us from Toulouse and telling us about electrochemistry at the nanoscale. Another really fascinating talk. Thank you, everyone.
Thank you. Thank you.
And have a wonderful day or evening.
Yeah, thank you.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可